logging on. So let me briefly introduce our speaker today, Professor Lei Wu. He's currently assistant professor at Peking University School of Mathematical Science and also Center for Machine Learning Research. Lei, he got his PhD from Peking University and then did his postdoc at Princeton University. And his research is focused on mostly on theory of deep learning that includes approximation of deep neural networks and convergence and implicit bias of SGD, which is a topic today, and also foundation models and transformers. So now the stage is yours. Hey, please go ahead.
Okay. Thank you for the invitation. Yeah. So in this talk, I will introduce our work on understanding the implicit bias, or sometimes also called implicit regularization of SGD from a dynamic stability perspective. This is a joint work with Professor Yi, Ma Chao, and Professor Su and Minze from Peking University. So in machine learning, there's some very situations when the model is over-parameterized. In these situations, it's actually very common, in particular before the large language model because dominates the community. For example, in the ImageNet, we have around 1 million images, but actually the state-of-the-art models has much more parameters. For example, the ResNet 152 has 60 million parameters, which is much more than the samples. That means our model can easily interpolate all the training data. This factor actually raise a concern about the overfitting, because our model is highly over-parameterized. They can interpolate our data. So in the traditional machine learning or traditional mathematics, if we want to avoid overfitting, we always prefer to do some explicit regularization, like, and this is also popular in deep learning. Like in deep learning, we all has with decay and batch normalization, dropout, data mutation, different sort of techniques for doing explicit regularization. However, in deep learning, there's another form of regularizations becomes more interesting. That is called implicit regularization. It basically says that we didn't do any explicit regularization during our training. However, our optimizer has a certain associated implicit regularization, because the specific algorithm with a specific initialization actually can only converge to certain solutions. The algorithm is not doing a random search over the manifold of minimizers. It's actually only pick up some solutions which is determined by the form of the iterations of the optimizer and also the initializations. So in this talk, our focus is to understand how the optimizer pick up solutions in the minima manifold. So let's first take a look at how important is the implicit regularization. So in this figure illustrates the training of the CFAR10 dataset by using an inception network. So the blue curve corresponds to training with base normalization, and the red curve corresponds to training without regularization. So no matter adding regularization or not, we can always get 100 accuracy for the training. And for the testing, we can see that even without any regularizations, our model can also achieve the accuracy around about 85%, which is much better than the random guess. Because in this setup, in this model, the network is highly over-parameterized. Our model actually can interpolate all the training data arbitrarily with random label. That means our model actually, there's certain solutions on the manifold, minima manifold, that actually generalize as it's not better than random guess. However, our optimizer SGD, which with a specific initialization does not select these bad solutions. It actually converts a solution which is much better. It's at 85%. And even more mysteriously is that in practice, we find that SGD actually performs better than GD. For example, in these tables, it's illustrated that the GD has accuracy about 95%. However, the full batch GD with well-tuned training learning rate and well-tuned step size, the number of epochs, it can only achieve about 87% accuracy, which is much lower than the accuracy yielded by SGD. So the SGD is originally proposed to speed up GD, which is, in terms of computational cost. However, in practice, it's all observed that SGD also often generalizes better than GD. So another question in this talk is, I'm trying to explain what's the difference between the GD and SGD. The difference between them to lead to the difference in the generalization. So this problem is actually very challenging because the neural network is nonlinear and non-convex. So if you want to understand how the optimizer to choose the, how the dynamics of the training and converge to the different minimizers, that's challenging because it's non-convex and non-linear. And the previous studies, because of this non-linearity and non-convexity, so most existing theory in explaining this implicit regularization focus on some toy models. For example, in linear regression, we can prove that GD with zero initialization will convert to minimum L2 norm solutions. For binary classification, or in general classification, with logistic loss, like loss, GD will convert to the L2 mixed margin solutions. And also we can, because the linear and the binary classification are also convex problems, so the analysis is doable because of the convexity. And we can generalize this to some non-convex model, but still it's limited to some very specific model like matrix factorization and linear networks. But in general, because if you want to track the whole the entire dynamics, the entire trajectory, then the analysis must be limited to some very toy situations. However, in this talk, I will introduce a stability analysis, which can which is not limited to toy models and also can explain some because in the practice has another very important observation about the implicit regularization of SGD, which is if you take a larger learning rate and a small batch size, they always need to better generalization. Why finite larger learning rate and a small batch is better for generalization cannot be explained by this kind of trajectory. No, this kind of analysis. Okay, so basically, in our attack is by doing some very preliminary stability analysis. So basically, we are trying to classify the fixed point of the SGD dynamics, and we can, because the different fixed point has some is stable, some is unstable, and SGD will only convert to stable minima is, it's just a very common procedures in the analysis of a nonlinear dynamic system. Because if you cannot track the dynamics, you can always do some fixed point analysis and do some linearization of the dynamics around the fixed point and analyze the linearized dynamics to get some stability condition, and you can classify the fixed point into some unstable ones and stable ones because your dynamics will only convert to stable ones. But in this talk, we have two tasks, which one is to analyze or characterize what do you mean by stable, and what's the stable minima for neural networks or for SGD. Another one is why stable minima generalize well. So basically, we have two tasks. To connect the stability and the generalization, I will introduce the concept of sharpness or flatness. The sharpness flat minima hypothesis is very successful empirical, mostly empirical theory to explain the implicit regularization. Basically, it says that SGD converges to flat minima, and the flat solutions generalize better. So this is a figure. This is it's just look at the blue curve. The blue curve. So we have this is the curve correspond to the landscape between the linear interpolation between SGD solutions and GD solutions. Alpha this point corresponds to the GD solutions, and alpha equals to 0 corresponds to SGD solutions. You can see that the SGD GD solution, the local landscape of GD solution is much sharper than the local landscape of SGD solutions. So this is very consistent observations. In practice, you can do some experiment to test the local landscape of SGD solution and the GD solutions. The empirical observation is that SGD always converges to much flatter solutions. And we need to specifically answer two specific questions. One is why SGD prefer flatter solutions. Another one is why flat solution drives better. For the first question, our answer is that stability, because SGD actually can only converge to stable minimum, and the stable minimum must be flat. So, in a summary, and our study actually is inspired by empirical phenomena, instability and escaping phenomena. So when I first do these problems, I'm trying to do some experiments. So this experiment goes as follows. First, I train the model. In this case, is a small convolution networks for fitting a corrupted fashion list. The corrupted means that there's some labels in the data set. The data are randomly labeled, partial of the data. I first train the model by using GD. When the GD nearly converge, I switch the optimizer from GD to SGD. You can see that SGD, instead of continually converge, SGD escape from the GD solutions, from the region GD converge, it escape and then converge again, converge slowly again. And moreover, SGD converge the solutions which generalize better. There's two observations. The first one is that this means the SGD, GD, the solution selected by GD is actually unstable, dynamically unstable for SGD. Moreover, the instability, I mean that the escaping, the SGD escape from the GD solutions, the escaping is unreasonable fast. Actually, the escaping happens in just a few iterations instead of a few epochs, just a few iterations. Mostly just the 10 iterations is sufficient for SGD to escape from the GD solutions to a region which is corresponding random guess, like 10% accuracy. So basically, that means the stability relevant. These experiments at least explain that the stability is relevant to distinguish the solution selected by GD and SGD. So then a natural step, next step is to analyze what kind of solution selected by GD by analyzing the stability. So analyzing the stability of SGD update is given by the following iterations. So let's look at the cartoon. This cartoon, this is the corresponding landscape. So we know that the A, B, C, D are they are all fixed points of the gradient descent. But the gradient descent can only converge to the local minimum C and D, because the A and B A is a maximum, B is a set point. They are not stable for GD. However, if the learning rate eta is large enough, the sharp minimum C can also become unstable for the GD, because we can do some, because if the learning rate is large enough, intuitively, if large enough and the minimal value is very sharp enough, the one step will goes to the another side of the value, and with a higher loss, then the converge will becomes impossible. The GD will just blow up. And if the local region is flat enough, they will converge gradually to the truly global minimum D. And this phenomenon can be characterized by linear stability analysis. So basically, it's a very simple. We can always linearize our dynamic system at the global minimum of interest. Wait, let's use theta star denote the minimum of interest. Then for the linear dynamics, we always have, we can explicitly calculate the iterations and gather the solutions. So if we want a linear dynamic system is stable, we must impose a condition that is this matrix, the spectral norm of this matrix is not greater than 1. And this gives us a condition that is the maximum eigenvalue of the Hessian must be controlled by 2 over the learning rate. So this is a very simple analysis tells us that stability actually controls the spectral norm of the Hessian matrix of selected minimums. That means the GD solutions. And moreover, if this condition is violated, then the GD will escape from that minimum exponentially fast because the linear dynamics, either converge exponentially or blow up exponentially. And more interesting, okay, this is just a very simple mathematical derivation. If you want to, so then we are interested in how this stability condition is relevant for practical training of neural networks. So I did some experiments in training in this table. So basically, I trained I using a small VGG networks. It has about 5 convolution layers, and to fit in the fashion analysis and the sigma 10. It's actually just a partial sigma 10. And by using the different learning rate. And if you look at, that's a very mysterious observation. That is, if you look at, for example, the learning rate of 1.0, okay, the upper bound of the maximum eigenvalue of the Hessian is 20. If you then the table, the cells, the value of this one is correspond to the maximum eigenvalue of the Hessian of the GD converged. So we can see that the GD, the sharpness of the GD instead is not only smaller than the upper bound, it's actually very close. It's nearly equal to the upper bound. So this means that the GD actually occurs on the edge of stability. So basically, the GD in the training of neural networks, the stability condition is not only satisfied. Actually, the GD training is on the edge of stability, not only satisfies the stability condition. Okay, so that means, so basically, you even before you train your neural networks, you can even predict the model, the sharpness of the converged solutions. So that means this is actually very relevant for the real training of neural networks. But I didn't do very sophisticated, detailed investigation of this phenomenon. But if you are interested, you can look at the following follow-up works on for these 2 papers, from these 2 papers on this striking phenomenon. Now, the actual question is, what about the SGD? For SGD, let's just unify some notations. Like I will use Li denote the fitting errors on the I samples. The SGD is given by this one. The B, capital B, denotes the batch size. And then I will make for analysis simplification. I make an assumption over-parameterization assumption. That is the loss of the minimizer is 0. Under this assumption, that means at the global minimum, each sample has 0 loss, and then gradient of each sample is 0. And this is guaranteed that all the global minima are actually the fixed point of SGD, because because at the global minimum, each sample gradient is 0. Then no matter how small the base size is, the mini batch gradient is always 0. That means all the global minima are the fixed point of SGD. Then you can do some linearization of your dynamics around the global minima, and okay, actually the linearization dynamics correspond to a linearized model. That means it's your model is linearize your model from around the global minimum theta star, and then if you only train the theta minus the theta star, SGD for training this linearized model corresponding the linearization of your original dynamics around the theta star. And for understanding, it's more intuitive to write your dynamics as follows. So basically, you decompose your stochastic gradient into the full batch gradient plus the noise, and I will use the sigma theta to denote the covariance of your noise. Then a very simple calculation tells that for just one step, the change of your loss is given by the following equation. So basically, the loss of the next step is consists of two terms. This term is determined by the full batch gradient. This term, and this term is corresponding the contribution of the noise. And particularly, we are interested in how the noise, the stochastic gradient noise, affects the stability. Then the problem is how to study what's the magnitude, what's the value of the nu theta. Nu theta is given by the trace product of the Hessian with the noise covariance matrix. So that means the noise contribution into the stability. Here, the stability here means the change in terms of the loss dynamics, which is determined by the alignment of the noise covariance with the local Hessian, because we are looking at the inner product, trace product between them. So then this inspired us to characterize how the noise covariance and its alignment with the local Hessian. To motivate, we consider regression situations, consider regression problem, and we can write the SGD as follows. Here we use the sigma t denotes the noise corresponds to the base size of 1. Then sigma theta is the noise covariance correspond to the base size of 1. And then this is the expression of the noise covariance. We are trying to understand what's the connection between this one with the local Hessian. And for the regression problem with square laws, there's a very nice property, that is Hessian has a natural connection with the empirical feature. So basically, Hessian can decomposed into two terms. The first one is the empirical feature matrix, and another one is this guy. And this guy diminishes at global minimum, because at the global minimum has the fitting error is 0. So this guy is 0. Then we have the H theta star is equal to the G theta star. G theta star is the empirical feature matrix. Also, sometimes we call it Gauss-Newton matrix. So in the next, we will study actually mostly interchangeable between these two terms, because in the small error region, they are very close to each other. And moreover, the G theta is always well defined in terms of the G theta is always positive semi-definite. However, H theta is actually not positive semi-definitely, in the whole landscape. It's only positive semi-definite at global minimum. So let's recall the loss. If I use EI to denote the fitting error at the I sample, we can simplify the loss as the average of the EI squared. And then we can look at the decoupling approximation, which is just a heuristic approximation. So basically, the noise covariance equals two terms, which this is the the covariance term minus this is the second moment minus the square of the first order moment. If at the global minimum, the full batch gradient can be if you believe it's much smaller than the sample gradient, just can have this approximation. And then you also believe that the fitting error eta, the sample fitting error eta, and the model gradient. Here the gradient f is the model gradient instead of the loss gradient. If we believe EI and the model gradient are decoupled, we have the next approximation. After this approximation, we have that the sigma theta is equal to 2 times the loss times the empirical feature. Okay, this term is actually exactly the empirical feature, which is the first part of the Hessian matrix, which also becomes the Hessian matrix at exactly global minimum. So this tells us that very intriguing property of the noise covariance. So in terms of magnitude, the noise magnitude is proportional to the loss value, because at the large loss value corresponds to larger noise, small loss value corresponds to the small noise. And in terms of directions, the sigma theta is aligned with the g theta very well. More specifically, that means noise concentrated on the sharp directions. So that means in the sharp direction, the noise energy has more spend more on the sharp directions. Along the flat direction, that's small noise. So specifically, if you look at the noise component along the direction of the V, is given by this guy, this noise energy. So that is equal to this equations. And because of this approximation, we have that the noise magnitude along the direction of V is equal to the 2 times of the loss times the curvature. So this guy is actually the local landscape, or the curvature of the local curvature around the direction, the V. So that means the noise magnitude along the direction is proportional to the curvature along that directions. Of course, this is a very heuristic approximation, which cannot be true in general, right? But it's very intuitive, and actually, we can make it rigorous by defining some much more weaker matrix to qualify the alignment. So because in this here, we qualify, we say if they are equal, actually we have one, because in the high dimension, for the model with many parameters, the sigma theta is a high dimension matrix. So this equation is impossible to guarantee this equation, this approximation is accurate. However, we can define some much weaker matrix to quantify this alignment, which is possible. So here I use alpha theta and beta theta to quantify the directional alignment and then the magnitude alignment. And lastly, I will use the mu theta, which is the multiplication of the two alignment factors. Specifically, I call this is the low-scaled alignment factors. If the decoupling approximation holds, we will have the mu theta is equal to 1. But this is nearly impossible. But I will convince you that either theoretically, for both theoretically and empirically, that this mu theta is actually is larger than is bounded from below by some constant mu 0. This constant is independent of the level of over-parameterization. Okay, just let's assume this alignment is valid. Then we will have, let's look at the stability. So for the one-step loss update, if we just omit the GD contributions, just look at this guy, the noise driven instability, noise driven terms, we will have this guy. And by assuming the alignment, we have this guy is actually greater than this term. So we have that the loss update is determined, it's multiplicative, and with a factor determined by the batch size, learning rate, and the alignment factor, and also the sharpness, but in terms of measured by the probability of the Hessian instead of the spectrum. If we want the dynamics stable, we must have the necessary condition for the stability is that this term must be smaller than 1, smaller or equal to 1, right? So this gives us that the probability of so if we assume this is not greater than 1, then we will have that. And also we assume that the alignment, noise alignment holds. Now we have that the probability of the Hessian at the global minima of selected by SGD must bounded by this quantity. Okay, for this quantity, it only depends on the batch size, and the learning rate and alignment. So basically, you can say that the small batch and the larger learning rates and the strong alignment will lead to smaller upper bound for the stable the Frobenstein of stable minima for SGD. And the most important fact observation is that this upper bound of sharpness is independent of the level of over-parameterization, in particular the sample size and the parameter size. So no matter how over-parameterized, no matter how wide, how deep your model is, how many your parameter your model has, as long as you use a constant, fixed learning rate, for example, learning rate 1.0 and the base size, some base size that's 200, then your model, your SGD can only converge to the solutions with the sharpness bounded by a constant, independent of your over-parameterization. And also, there's another interesting observation that if we compare SGD and the GD, for the GD, the stability can only control the worst sharpness. That means the spectrum. But for SGD, the stability can control the whole spectrum by control the Frobenstein of the Hessian. And then, okay, so now by assuming the alignment, we can already show the SGD in fact impose a much stronger sharpness control than the GD because it can control the whole spectrum. And then the next question is why, if the alignment holds in practice or theoretically. So without giving some detail about the proof, but we can prove that for deep linear networks, we can prove that the mu theta is bounded from below by constant 1. So we can prove that for linear networks, this alignment, noise alignment indeed holds. And also we can prove for the nonlinear networks. But here we consider nonlinear network, which is the outer weight is not learnable. The AJ is either -1 or +1. So this model is okay. It's kind of limited, but this model still has the universal approximation property. It's very common used in theoretical analysis. If the sigma activation is the liquid rule with the non-degenerate gradient derivative, and as long as the sample size is large enough, we have that for these nonlinear networks, the noise alignment still holds with a lower bounded. It depends on the alpha and the beta. Okay, of course, but theoretically, this lower bound depends on alpha beta, but in practice, the practical empirical observation is actually it's always close to 1. It's a lower bound, always close to 1. And then what happens if the stability condition is violated? Okay, then the simple derivation tells us that if this is stability, so basically, if we denote this quantity called the gamma 0, then by the induction, we will have that the loss will, if this quantity is larger than 1, because just one step, the loss will increase by a factor larger than 1, then after many iterations, the loss will blow up exponentially. So this gives us that if the stability condition does not hold, we will have the loss will increasing exponentially fast, and with the factor depends on this guy. And then this exponentially escaping, this means that the noise-driven escape is actually exponentially fast. This explains our previously observation that when we show just previously, so the escaping is just happening in just a few iterations. This intuitively, this is because the noise covariance, the structure of our noise covariance. So first, why the escape is exponentially? It's because the noise magnitude is proportional to the loss value, intuitively. Because, for example, if you start from the small loss regions, and then if the stability condition is not satisfied, then you will go to a large a region with a larger loss value. And because that larger loss value means the larger noise, and larger noise means larger perturbations, and then you go to much larger loss value regions. So this give us a positive feedback. You will goes up exponentially fast, and moreover, this exponent gamma 0, this factor gamma 0 is independent of the dimension d. Okay, that means the escaping is equally efficient, no matter how high dimension the model is. So this is these two factors. So basically, this the material structure determines the escape is exponential, and the directional alignment determines the factors of gamma 0 is independent of the parameter, the dimension. And if the noise is uniform bounded, actually you can prove that. If the noise is not loss dependent, it's uniform bounded, you can prove that the loss increasing at most linearly with respect to iterations. So here I just provide some more detailed experiments for the linear network, fully connected network, and the convolution network. You can see that for all the models, the SGD escape from the global minimum just exponentially. And for example, in this case, the loss increasing from the 10 to the minus 8 to the around 10 to the minus 2 for just 9 iterations or 10 iterations. The escaping is indeed exponentially fast. And we also can empirically verify our noise alignment. That, for example, here I consider linear networks also still linear networks, fully connected network, and the convolution networks. So this is a small scale experiment because the model has at most, if I remember correctly, 100 about 1 million parameters. So you can see during the training, the mu theta is close to 1, and for all the model, for all the 3 models. And moreover, if you look at the second rows exam how the alignment change with the over-parameterization of our models. So as increasing the model size, the alignment actually is nearly unchanged. Of course, even increase for the linear networks. And for the convolution networks and the fully connected to the network, we indeed can observe some, very small, very tiny decreasing of the alignment, but it is still very, bounding from below. Even when the model increasing to the 1 million parameters. And moreover, this is just a small scale experiment. It's for training partial of the CIFAR-10 dataset and the MNIST. But if we look at the more practical models, in this slide, I present the experiment for practical models. I mean, practice here means the ResNet and for the full CIFAR-10 dataset. So let's look at, for example, let's look at the first row. First row shows how the upper bound, the necessary condition upper bound, and compare with the solution, the proportion of the solutions of SGD, the true sharpness and the sharpness upper bound given by our theory. You can look at that for the other situations, the upper bound are actually very close. Okay, maybe not accurate to say they're close, but they are under the same orders. And moreover, as for the larger models, the bound becomes much tighter. In particular, for the VGG19, the bound actually, the upper bound becomes nearly exactly the same as the true sharpness. And in the second row, we examine how the upper bound changes with the batch size. So you can look at for the small batch. If your SGD using smaller batch, the upper bound is actually much close to the truly sharpness. Okay, this is because this actually can be explained by in our derivations. Because in our derivation, I only want to derive some necessary conditions. So for simplicity, I just omit these GD contributions. So this necessary condition is doomed to be not tight enough, very tight, because omit of this term. However, if your batch size is small enough, the contribution of this term should be negligible compared to the noise term. If your small batch size, the batch size is small enough. So this explains why our bound is much tighter for small batch training and some relevant rules for large batch training. So, okay, so our stability argument so explain why SGD and GD prefer flat minima, and also we already see that the stability actually means for GD and SGD they both prefer flat minima, but the flatness and sharpness is measured in different matrix. Then the next question is, because our ultimate objective or the aim is to understand the regularization. So next question is why stable minima generalize well. So because we already essentially the question is why flat minima generalize well, because we already show stable minima is flat. Then the question is why flat minima is generalizable. So the popular explanation in the community is given by this figure, illustration figures. The black curve corresponding to the training landscape, the red curve corresponding to the testing landscape. The training and testing has some deviation because the finite sum effect, there are some difference. So you can see by this illustration, you can see for flat minima is robust to the small deviation. So a small deviation between the testing and the training, that means the robustness means that the flat minima in the testing landscape, it also has a very small error. However, sharp minima is actually non-robust to the small deviation. So because this sharpness, they are non-robust to this deviation between the training and the testing landscape. This point corresponds to the the loss in the testing landscape is given by this guy. Is as illustrated, is very large. So this is a very intuitive illustration why flatter minima and generalize. However, this illustration is actually very misleading because essentially it's not trying to explain why flat minima is generalized well. It's actually trying to explain why sharp minima does not generalize. However, this is not true. It's untrue because sharp minima actually can generalize very well. This is the case for the deep ReLU networks, because in the ReLU networks, ReLU activation has a positive homogeneity. So for a ReLU network, you can always rescaling appropriately for each neuron the input, the inner layer weights and the outer layer weights without changing the implemented functions, without hurting the changing, altering the generalization. But these rescaling operations can drive your minima to another very sharp minima, even arbitrarily sharp. So in that sense, sharp minima can actually generalize very well. So that means, so this fact actually tells us that this is an illustration is actually misleading. So the reason is that in the high dimension, our model lives in the high dimension. The deviation between the training and the testing landscape can happen in very different directions. This is very different from these figures because they are moving in the same directions, in the same dimension. So you will have this observation, but if this deviation happens in a very high dimension, you can easily construct some situations, some deviation that is the sharp minima can also generalize well. But on the other hand, this fact that sharp minima can generalize well for the ReLU networks means that if we want to develop some theory, we can only guarantee that the flatness is a sufficient condition at most. Flatness is cannot be a necessary conditions. That means we can only say flat minima generalize well. We cannot say sharp minima does not generalize. Lastly, I want to remark that if we want to develop some theory, we still need to some specific parameterization of our models, because you actually can construct models and the data distributions such that flat minima also generalize worse, generalize very badly. For example, in the Zhiyuan and my papers, we can construct some. So in my papers, I construct some artificially machine learning models, which never used in practice, but in that models, the flat minima drives very badly. And in Zhiyuan's paper, they still consider the two-layer neural networks, but they make some assumptions about the input data distributions. In that data distribution, the flat minima actually drives very bad. So that means it's impossible to develop a general theory try to say that for a very general model, very general distributions, we can show the flat minima drives well. This is impossible. If there's this kind of theory, there must be some fake theory. So so I personally I also do not have a general theory, but we can get some intuition from some specific models. So specifically for this case, if we look at the two-layer neural networks and the ReLU activation, if we assume the input to be a uniform distribution over the sphere, then we can prove that as long as the data sample size is bigger than the dimension, we will have that with high probability. The spectrum of the Hessian is roughly equal to up to some constant is equal to the L2 norm of our parameters. And the Frobert's norm is equal up to some constant is equal to the weighted L2 norm. And also the trace of a Hessian is equal to another weighted L2 norm. So I will use this notation to denote the weight L2 norm with the gamma, denote the weights between the inner layer and outer layer, the weights. So in this proposition, actually we establish the connections or the equivalence between the sharpness, the different matrix of sharpness, the different sharpness, and the parameter norm of our models. It's well known that for the two-layer neural networks, the capacity can be well controlled by the path norm. And also, we know that the weighted L2 norm can well control the path norm, because by the Kirsch-Schwarz, the 2 gamma L2 norm is bigger than 2 square root of gamma, the path norm. So we will have that. So combine them, we will have that observation that for two-layer neural networks, the stable minimum of GD must be generalizable. And then we can even get a generalization bound for the GD solutions, because the generalization, informally, the generalization gap is bounded by the path norm divided by the sample size. And then the path norm of the GD solution is upper controlled by the weighted L2 norm. And the weighted L2 norm, because of stability, GD, because of this proposition, the L2 norm is equal to the spectrum norm of the Hessian. So it's will roughly equal to the sharpness over the subsize. And because of the stability, we know that the GD, for the GD minima, stable minimum of the GD, the sharpness is smaller than 2 over learning rate eta. So we have that the stable minimum of GD solutions is bounded by 2 over learning rate over divided by sample size. So we can say that no matter how over-parameterized our model is, as long as you are using a finite learning rate eta, the GD solutions must be generalized, must generalize well, and without dependence of the sample size, the parameter size, the input dimension. And similarly, you can get the similar guarantee for the SGD solutions. And okay, so I already said that. However, this model, for this model, they cannot explain why SGD generalizes better than GD, because Frobert's norm and the L2 norm give us the same control, and not exactly the same, but they are both give us effective control on the capacity of our models. We can look at another model. In this case, the GD stability, the stability of the GD and the SGD give us a totally different control of the capacity. This is the diagonal linear network, which is actually just a linear regression with the coefficients re-parameterized by the multiplication of two factors, two parameters, AJ and BJ. So this is just a linear regression with re-parameterization. But with this re-parameterization, the landscape becomes non-convex. Do you know about alpha? Is this guy? Oh, this production means element production. This O times means element production. So alpha is a vector of a dimension D. We can prove that the L2 norm of the Hessian is roughly the L infinity norm of the alpha. The Froebel's norm is roughly the L2 norm of the alpha. And the alpha, the LP norm of alpha is can control the LP norm of our effective coefficients. So A times B, O times B. This is the the tuning the coefficients of our linear models. So this means the stability of GD can only control the spectral norm. Spectral norm means can only control the L infinity norm of our linear regressions. But the SGD can control the Froebel's norm, means that SGD stability can impose a ridge. Okay, the L2 normal control corresponds to the ridge regression. So that means SGD can impose the ridge type capacity control, but the GD can only impose infinite. For linear regression, F infinite norm cannot provide effective capacity control because the dependence of the dimension will becomes explicitly if you only control the infinite norm of our coefficients. And this is product experiments. But in this case, you can see that when we increasing the learning rate, so when we increasing the learning rate, our the stability control becomes stricter. Then that means the solution is flatter. So you can see that when increasing learning rate for SGD, the solution becomes much better and better and better. However, for GD, the generalization the generalization is very bad, and also the generalization performance does not increase with the learning rate, increasing the learning rate. This is because the GD, the stability can only control the L infinity norm of effective coefficients, which is not sufficient to guarantee generalization. But for SGD, the capacity control is effective. So in the summary, okay, so we provide a stability perspective to explain the implicit regularization. So basically, we are trying to say that SGD only selects the stable minima, and stable minima is flat, and flat minima drives well. And particularly the non-trivial aspect is that we find that SGD noise is highly anisotropic. It aligns well with the local geometry. And this property we believe can be very important for in general for the analysis of the SGD dynamics beyond the property of the generalization. And also we show that, okay, we already, another important observation is that the stability control ensure that the sharpness of stable minima is bounded independently of the level of over-parameterization. And also we provide two specific models to illustrate how the stability control impose effective capacity control for the generalization. Yeah, this is all my talk.